So with the scientific method, it's very important to keep this in the context of the real world. When we looked at this in the beginning of the year, we talked about how scientists doesn't just show up one day and say I'm on step 3 today. It's a very fluid process, but every good scientific investigation has these 4 steps, and yeah, it's important to consider those. And so with the Large Hadron Collider, the particle accelerator, they started to make observations, of the world, and seeing these particles coming from the sun. Then he started, actually intentionally smashing particles together, coming up with a standard model, and then eventually, said, yeah, we think we have a pretty good model here. They made a hypothesis about the Higgs boson that, it's the particle that will complete the standard model. They tested it, they interpreted results, actually found it, and then concluded that. And so there's still many unanswered questions. So we're still coming back up here, making more observations and trying to understand, the fundamental interactions in the universe. So it's important to remember what a theory is. Remember, theories try to explain why, and laws describe what happens, right? So in a theory, we're trying to explain, again, why things happen. Laws describe what happens. Okay, so with linear motion, the first thing that we talked about is speed. Speed is how much distance we cover in a period of time, and we get meters per second for that. There's no direction with speed, right? We just, like with a speedometer in a car, it just tells us how fast an object is going. And with velocity, however, we're looking at displacement in a period of time. So, how much displacement we cover, and that's in meters per second. And so in class, we looked at different examples. I had them come up with an example of where speed and velocity are different. If we had a race and let's say we started right here and we went all the way around and we ended up here, well, our average velocity would be 0 because our displacement is 0, even though we have, we get a period of time. But our speed would not, right? Because distance over time, we'd have a certain amount of distance. So we must have direction with velocity, and displacement is a vector, velocity is a vector. You have to have direction with vectors. Okay, so acceleration is how velocity changes in a period of time, meters per second squared. It's also a vector, and we look at how velocity changes in a period of time. So yeah, for this graph here, what I want you to do is to find the velocity during each time interval, and then pause the clip and do that. And then during what time interval is the speed the greatest? And to kind of review a little bit, remember slope is equal to rise over run, and then velocity is delta x over t, right? So the rise is delta x and run is time. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. All right, so for that first section there, the rise is 2, the run is 2. We get 1 meters per second for our velocity there. And then for that middle portion there, we're staying at 2 meters. We're not moving, so the velocity there is 0. The final one is -2. It falls, final position is 0, the initial position is 2, and so the velocity is -2. And the speed is greatest during that time interval, because remember, speed has no direction. What's just the greatest amount? And so the speed is 2 meters per second during that 4 to 5 second interval there, and that's when the speed is the greatest. All right, for this one, what is the acceleration from 0 to 2, from 2 to 4, and from 4 to 6? So again, with this one, remember, acceleration is the change in velocity over time. So our rise is velocity, our run is time. Go ahead and pause the clip and try these, and then when you're ready to check, you can hit play to continue. Okay, so during that first portion, there's no change in velocity. The car is moving, at a constant 10 meters per second. So it's definitely moving, right? It's not staying in the same position, which that's a very common misconception, is to look at a velocity graph and like, oh, it's a flat line, so it must not be moving. But yeah, it's moving at positive 10 meters per second as it goes across there, and we've got that. During the second portion here, our rise is 30 meters per second minus 10 over 2. So positive 10 meters per second, the car's getting faster. And then the last one, yeah, the car's not getting any faster. It's staying at 30 meters per second, so it's moving very rapidly, but again, you know, it's not changing velocity, so there's no acceleration. All right, so if you remember with our equations, right, so speed is distance over time, velocity is delta x over t, and you know, we have yeah, we can use these as long as our speed and velocity stay the same. But as soon as it changes, right, if we're getting faster or slowing, or if we're turning, we have to use one of our three constant acceleration equations. Really, this is not really an equation. Yeah, so we can use one of these three and we can figure out what we need. And we have those on our equation sheet. It's just this one looks a little bit different. It's v final squared equals v initial squared plus 2a delta x. That's just rearranging the equation there. Okay, so for this one we have a car that's 14 meters per second on the road. Traffic light turns red and it takes 4.5 seconds to stop. We want to find the car's acceleration. And so yeah, for this one we know those variables, and so see if you can figure out which one of those three will help you find the acceleration, and you can do that. So the biggest thing here is identifying which those variables are and doing that. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we should get negative 3.11 meters per second squared. The first equation on that list works. We know the final velocity, we know the initial velocity, we know how much time it took, so the acceleration therefore would have to be negative 3.11, and that should make sense because the acceleration is negative, the velocity here is positive, and it's going to slow down there. All right, so for this one, I'm going to let you set this one up on your own. Go ahead and draw it, identify the variables, and then see if you can find the equation, acceleration equation to solve this one. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so you set this up, delta x is 700, acceleration is negative 13 meters per second squared. It's going to come to a stop, and we want to know the initial velocity. So we can use v final equals v initial plus acceleration times time. And again, just rearranging the equation, we get that, and we should get a velocity of 134.9 meters per second. Because we set up things left to right here, acceleration is negative, this would be positive 134.9. So that's the velocity as it you know, touches down and then comes to a stop.